Section 7.3, Simplifying Radicals by Factoring. Simplification of a radical is complete when all factors in the radicand can be written with exponents less than the index. And here we have, in this first example, the square root of 200. We're actually going to use the product rule to simplify this. But first, let's break 200 down into a product of numbers that perhaps has a perfect square in it that is equal to 200. Well, we can break this 200 down into 100 times 2, where 100 is the largest perfect square factor of 200. Then, using the product rule, we can break this into the square root of each of those factors and simplify it from there. The square root of 100, since it is a perfect square, since 10 times 10 equals 100, we can replace square root of 100 with 10 and leave the square root of 2 as is, since there is only one 2. This is known as simplified radical form. In the next example, using that same technique, looking for the largest perfect square here, since 75 is 25 times 3, we can replace 75 with 25 times 3. And looking for perfect squares here in terms of the variable, x to the 5th can be broken down into an x to the 2nd times an x to the 2nd times an x. If you multiply those common bases together, we do have the equivalent of x to the 5th power. Now we can take the square root of those perfect squares. I'll put the 25 and both of the x squareds underneath one radical, and the values or the factors that aren't perfect underneath another radical. We still have the same factors. This would multiply to give us a 75x to the 5th power, but we can simplify. Replacing 25 square root of with a 5, since 5 times 5 is 25, we have 2 or a pair of x squared, so the square root of x to the 2nd is x to the 2nd, and leaves us with the radical that we can simplify with the radicand of 3x. So our final answer here is 5x squared times the square root of 3x. Another way we could have gone with simplifying this is the square root of x squared would have brought an x out in front. The square root of x squared would have also brought an x out in front or out from underneath the radical. Those two x's, x times x, would result and simplify into an x squared. In this next example, we have a cube root. Now we're looking for perfect cubes. The largest perfect cube that is a factor of 80 would be 8, and 8 times 10 is 80. Looking for a perfect cube for y to the 7th, we could break that down into y to the 3rd, another y to the 3rd, and a y, all underneath the radical here. Again, verify common bases multiplied together, add your exponents. 3 plus 3 plus 1 brings us back to the 7th. And just as a shortcut then, instead of separating out these factors into two radicals, we can just simplify from here. The cube root of 8 will give us 2. Cube root of 10 we can't do anything with. It'll remain underneath the radical. Cube root of y to the 3rd power will bring out a y. Cube root of y to the 3rd brings out another y. And we're still left with the y to the 1st power. So 2 is the square root of 8, y to the third. The cube root is y, same with this other one, and left underneath the radical is the 10 and the y. If you're having difficulties seeing where y to the third is coming from, we could take this a step further, and let me show you the entire prime factorization of this radical. Cube root, we're looking for 3 of a kind, and let me get my radical long enough here. If we do a prime factorization, 8 would break down into 2 times 2 times 2. 10 is 2 times 5. And then we have 7 8s multiplied together, or 7 y's multiplied together. So let me get 7 y's multiplied here. And I think I have them, 2, 4, 6, 7. All right. Now, when we're looking for a cube, we're looking for 3 of a kind. So here is a 3 of a kind. What times itself 3 times is equal to what originally was the 8 is a 2. So the cube root of these 3 factors brings out a 2. We only have 1 2, we only have 1 5. Again, we're looking for 3 of a kind. Here is 3 of a kind, which means out comes the y. Y is the cube root of y to the third power. Here's a group of 3. That will bring out a y as well. And we still have only 1 y remaining. So here's that value left underneath the radicand, the 2 times 5 times y, or the 10y. And cleaned up, we most likely would write 2y to the second power times the cube root of 10y for our final answer. In this next problem, we are looking for the largest perfect fifth root that goes into 96. And if you do some calculating, it turns out that there are a bunch of 2's in 96. And to help with that, you can do your prime factorization. And it turns out that 96 is the product of 32 times 3. 32, if you break that down, is 2 to the fifth power. 2 times 2 times 2 times 2 times 2 is 32. Same thing we did with the last problem we can do with our variables here. Y to the third, or x to the, I don't know where y to the third came from, but let me try it again. X to the 8th power is x to the 5th times x to the 3rd, if I break it into a perfect 5th root. Y to the 6th, I'm going to break it into a y to the 5th with a y to the 1st, and a z to the 15th. We can have 3z to the 5ths, which multiply together to give us our z to the 15th. So we have it broken down to help you see it visually. The 5th root of 32 is a 2. There's only one 3. We'll leave that underneath the radical. The 5th root of x to the 5th means x is the perfect 5th root. X to the 3rd, not high enough power, but y to the 5th is. The 5th root of y to the 5th is a y. Not enough with the y. And each one of these z to the 5ths will bring out a z for each one of those, leaving those factors that didn't have high enough powers. We have the 3, we have the x to the 3rd power, and the y. We can simplify this. Instead of writing 3 z's multiplied together, we can write this as 2x, y, z to the 3rd power, 5th root of 3x to the 3rd power y underneath the radical. Now, we can convert these radical forms into rational exponents and try to do this mentally. If you're noticing what's happening here and using the conversion to a rational exponent, I'm going to ignore the number right now, but looking at just the variables as a shortcut here, this is 96 x to the 8th, y to the 6th, z to the 15th is, this whole quantity is to the 1/5 power. And as I said, I'm going to ignore, excuse me, I'm going to ignore the 96 to the 1/5 power. We handled that here by using our prime factorization. But if you look at the exponents, and what we have is a product raised to a power. So each one of these is raised to that 1/5 power. The index becomes the denominator of our rational exponent. So we have x to the 8th raised to the 1/5, a power raised to a power we multiply, which is 8/5. Likewise, y to the 6th raised to the 1/5, you multiply 6 times 1/5 is 6/5. And z to the 15th times 1/5, 15/5 gives us a 3. If we go back and we simplify this, how many times does 5 go into 8? 5 goes in once with 3 left over. And here's what we ended up with. Here's our x to the first. We have a whole group of 5 x's multiplied together, which is the 5th root, and 3 were remaining. And notice what's underneath the radical, x to the 3rd power. When we move to the next one, y is to the 6/5 power when we're taking the cube root of this radicand. 6 divided by 5 is 1. In other words, there's one group of 5 y's multiplied together, and here it is, y to the 1st power with 1 left over, and that 1 left over remains underneath the radicand, radical sign in the radicand. And the last one, we had z to the 15th times 1/5. 15 divided by 5 is z to the 3rd. And notice what's here as our coefficient and simplification of this radical. So you may want to try to do this mentally with simplifying initially to see what's going on, writing them all out, and circling the groups, whatever the index happens to be, could help with your understanding of what we're doing.